Good afternoon, everyone. Today I have the great pleasure to welcome Professor Dilip Asthagiri. He graduated in chemical engineering from the University of Delaware and obtained his master's and PhD also in chemical engineering from the University of Michigan and the Indian Institute of Technology, Madras, respectively. Professor Asthagiri currently works as an associate research professor at Rice University. He is an experienced researcher with a distinguished track record working in higher education and collaborating with industrial partners. Research interests include chemical and biological physics, thermodynamics and statistical mechanics, theoretical chemistry, molecular modeling, and statistical inference and modeling of data. He is the author of over 120 journal publications that have been cited almost 3,400 times. So once again, welcome, Professor Asthagiri. Thank you so much for being here, and please feel free to share screen and start presentation.
Okay, thank you so much. I hope all of you can hear me well, and I'm going to try, and you cannot start sharing while other participant is sharing. Okay, so.
Okay, you can, now you can do it.
Okay, give me 1 second. Are you all able to see the screen, what I'm sharing? Okay.
Yes.
Yes.
Okay. First of all, let me thank Federico and the Atoms group for inviting me to this venue. I have been following some of the talks on YouTube, and some I have been able to attend in person. So it's been very educational and very informative. And again, thanks to also Thiago, who is a former Atoms group member who made it all possible for us. My voice is okay? Is the voice carrying?
Yes, it's okay.
Everything is okay.
So very good. So what I'm going to talk about today, the work I'm going to describe, covers about 16 years of work done over 3 different institutions, starting from Los Alamos National Laboratory, going on to Johns Hopkins, and now to Rice. And over this time period, we have built a framework to look at liquids and look at the phenomena of hydration. Okay, so the talk is going to be structured in the following way. What I'm going to talk about is, first I will give a brief introduction to the theory. Okay, then I'm going to talk about applications. Okay, the 2 applications that I'm going to look at are aqueous ions and proteins. There are a lot of intermediate solutes that I'm not going to focus on. And within the context of protein hydration, I'm going to look at temperature effects, going to look at modeling thermodynamics of a folding transition. And time permitting, I'll also talk about simulation, the implications of our work for just simulation models of how to be careful in doing simulations on proteins, and then summarize. Okay, and in the top corner, top of the panel of the slides, I'm giving a way for a navigation bar so that you know where we are in the talk. Okay. So we start with the idea of the potential distribution theorem, and I'm sure everybody is familiar with this. And I'm going to look at it for ease of presentation. I'm going to look at it in the inverse form. Okay. So essentially, I have a solute here, which is a red sphere, and the solute has an interaction with the solvent. In this case, it's shown as epsilon1, and as the solvent is sampling different configurations, I get a distribution of energies. Okay, and P of epsilon here is the binding energy distribution. So as you might know, a direct application of this relationship always runs into problem. And this is a well-known idea. And this happens because of the following feature. Okay, notice that the exponential weighting is the high energy tail is being required, but it is precisely the high energy tail that is poorly sampled in a simulation. In fact, these kinds of distributions that we see in simulations, these are at least the high energy tail part. These are extreme value distributions, and it is fairly difficult to sample these distributions. And it is precisely to deal with such distributions that you have ideas like thermodynamic perturbation and thermodynamic integration. What we are going to do is we are going to take a slightly different approach. And that approach goes back to an idea in both in physics and in statistical modeling, which is called regularization. So this is an ill-conditioned statistical problem. I'm going to figure out a way to condition this problem to make it better. And I do this by doing the following task. So I have my solute that's interacting with the solvent molecules. And what I imagine doing is I imagine pushing the solvent away from the solute to some distance lambda. Okay, and that lambda we'll treat it as a parameter for now. And as I move this solute solvent interface farther and farther from the solute, what you will find is this binding energy distribution of this conditioned or regularized solute becomes better. In fact, it will tend to be a Gaussian as you move it farther and farther away. And it is easy to deal with a Gaussian in the potential distribution theorem. But now we have a different problem. What we now have to do is to enumerate what happened in the close contact when the solute was in close contact with the solvent particles. And we are going to treat the local problem, which is this local contact between the solute and solvent, by enumerating states. And here is how we do this. So I'm going to focus on a neighborhood of the solute, some neighborhood, and this range is going to be defined depending on the problem of interest. And I'm going to just sit there and poll the number of solvent particles that enter. For example, in this schematic shown here, there are 3 solvent particles. And in this schematic, there are 4 solvent particles. So xn, x subscript n is the probability of observing an n coordinate state. And in the spirit of Stillinger-Weber significant structures, you can think of each of these n coordinate states as a particular basin of attraction. Okay. But what I'm going to do is I'm going to take this, I'm going to try and characterize this probability distribution. And for each of these n coordinate states, I'm going to be able to get a binding energy conditioned on the solute having that particular coordination number. Okay. So when I have these 2 ingredients, I can do the following. I can go ahead, and this was my original probability that I started with. And this is essentially, I'm constructing that original probability as a marginal distribution. Okay. And now when I can again take this probability here, stick it into the potential distribution theorem, and then I get this following partition function perspective of the PDT. So here this is the first change that happens. So we don't see the PDT as a tool to just get free energies, but now we see it as defining as a local partition function. Okay. And there is yet another nice feature of this PDT relationship. I can do this process going forward, which is what I showed here, because that's easier for you to understand. And you can also reframe the PDT as the more conventional particle insertion problem. And in that case, the probabilities are the uncoupled. These are the uncoupled probabilities. They are given the sign P's, P naught, P superscript 0 is the uncoupled probability distribution, binding energy distribution between the solute and the solvent. And now I'm polling the distribution of solvent. This is the behavior of the neat solvent. And I get these 2 relationships for the excess chemical potential of the solute of interest. These 2 relationships automatically define a fundamental identity. And this identity proves to be rather important. What this identity is telling us is the following. It's connecting the coordination states of the solute of interest in the solvent to all the neat solvent properties. This Pn is all the property of the pure solvent without any reference to the solute at all. And these are coupled by these chemical potentials. Okay. And just as one more thing I want to mention in passing is, if you take these 2 distributions, they themselves define, they are at the heart of, for example, Bennett's overlap methods. Okay. But we are not going to take that path but those ideas are already implicit in what we are doing here. So that is the relationship that we get between the xn and pn distribution from these two equations. And I'm going to now look at one particular member of this set. So n can be anything from going from 0 up to any maximum number, but the n equal to 0 value proves to be rather important and rather physically clearer. Okay, and the n equal to 0 member gives the following relationship, and it has a nice schematic description here. And this is yet another way to think about what we are trying to do in this problem. So you have a neat solvent, you blow a cavity in the solvent, and that gives you, and if the solvent is liquid water, that gives you all the hydrophobic contributions to hydration. Then you insert the solute, and this problem is well defined, and that gives you the long range contributions to hydration. And then you allow the solvent to slowly occupy the inner shell. Okay, and that gives you what we call the chemistry contribution to the process of hydration. So what we have tried to do is we have tried to recast the original ill-conditioned problem into 3 contributions that are much better behaved. Obviously, we still have the task of calculating these values, but here is where we start having, we can be creative in how we approach this problem. Okay, one particularly interesting way to do this is and that will become clear when I talk about ions, is to look at these as in terms of clusters. Okay, so what I have tried to do in these slides so far is to just give you an overview of the theory without going into too much depth. Okay, and throughout this development here, what I have tried to do is I have chosen the number of solvent particles as an order parameter in this development, but the order parameter can be anything. Okay, so and the order parameter can be anything, and we can define, provided we are able to define a suitable constraint to indicate that order parameter. And I'm going to generically indicate that constraint here as some chi. Okay, and so all of the relationships that I showed here comes from this central relationship, which we call the rule of averages, connecting the value of this constraint or the order parameter in the system where the solute is with the solvent, to the order parameter when the solvent is not there. When the solute is not there. Okay, and just for reference, we wrote a perspective on all this, and the reference is given below. So we have this theoretical framework. We have been using this as I mentioned, for the last 2 decades. And the problems the kinds of problems that we have managed to tackle with this framework have ranged from simple Hart spheres to Lennard-Jones particles, polar solutes, and we have this approach that I just sketched for you gives you an interesting approach to look at liquid water and the role of both short range and long range interactions in the thermodynamics of liquid water. In the talk today, I'm going to focus very briefly on monoatomic ions, and I'm going to look at proteins both folded and unfolded or disordered. And in passing, I want to note, because Walter Chapman did present his talk in one of the previous atom seminar, ideas from quasi-chemical theory have now been incorporated into the SAFT framework, where now the quasi-chemical theory allows you to take account of multi-body correlations. And this becomes what is known as the cluster expansion or the cluster distribution approach within SAFT. Okay, so again, just to give you an indication of the diversity of applications that we have looked at. So going forward, I'm going to start looking at some of the applications that we have seen. The first one I'm going to focus on are ions. Okay, so simple ions, and the motivations are quite ions have been, studies of ions in liquid water has been going on for over 100 years, and it will continue on, and it is still an important problem that we need to understand. Okay, and I chose this panel because both my PhD mentor is here and also Federico is here. For example, if you take lysozyme crystallization, okay, these are, if you see this, you see the solubility of lysozyme is fairly sensitive to the type of the ion. Okay, so how do we understand this? The questions are, how do we understand this? Can we predict it? Can we model it? The problems that were of interest to me were understanding why, for example, this KCSA potassium channel that is there in all of the excitable cells in our body, why does it allow potassium to go through and not sodium? Okay, and for example, why zinc fingers, which was another problem that we were looking at, why, for example, zinc fingers bind zinc but not iron or cobalt? And iron is far more bioavailable than zinc, but still Mother Nature figures out how to avoid iron in a zinc finger protein. So what is the physics in these systems? So for these kinds of problems, what you are faced with, especially for the zinc finger protein, you're faced ultimately with the idea of trying to describe chemical interactions. Okay, so now you have to, in fact, account for electronic structure effects. And so for this particular case, we are going to recast the quasi-chemical approach in the following way. And this is also the reason why we give the theory the name quasi-chemical. What I'm going to start off with is I'm going to say the solute. So I have my solute, which is the ion, and I'm having an inertial around the solute. Okay, and that inertial is initially empty. Then what we do is we consider the binding of n water molecules to this inertial, and we calculate this ratio, which is just the equilibrium constant. That is a standard, law of mass action kind of equilibrium constant. And if I know these equilibrium constants, I can compute x naught standardly. This is just a mass balance. So once I get this x naught, I can go back and stick this factor into the quasi-chemical in the framework that I mentioned, and we are going to do the following. We are going to make two approximations, and both of these, in more recent work, both of these approximations have been removed, but I'm going to stick with the earlier version where we did make these approximations. What I'm going to do is these are the equilibrium constants, assuming there is fluid everywhere. So this is an equilibrium constant in the bulk. But what we are going to do is we are going to get this quantity in assuming there is no bulk medium at all. So it's a fairly brutal approximation, but it works well for ions because the bulk medium doesn't play a big role in how the ligands or the water molecules pack around the ion. The second approximation we make is that we are going to be ignoring packing effects. And again, this approximation can also be removed. And now what we do is, after we get this relationship, we are going to bring all of what we know about electronic structure methods to calculate this guy. And the theoretical chemistry community has advanced to an extent where we can compute those values with a fairly good accuracy. And for this long range part, and this is again where theory provides us guidance, since the solvent is now no longer in close contact with the solute, the long range part can admit a more classical description. The ultimate classical description is a Born model, but we are not going to do that. We are just going to do this with classical force fields. Okay, so we are going to treat the bulk solvent as an SPC water model and find the free energy of this object of the ion with no water molecules within the inertia. And this would have been clear, but rho is the density of water molecules in the system. Okay, so here are some results. So we can go ahead and look at, this is an example for how this approximation works. Let me make one more point. This equation has to be independent of the number of solvent molecules that or number of water molecules that are there in the inertial. That is an example of, so I should be able to do this for 1, 2, or whatever, how many ever water molecules. I should be able to vary the cluster and still have a stable estimate of the free energy. And this idea is known as cluster variation, and it relates to problems in phase transitions. We borrowed that idea here. And what we are going to do is the following. We are going to look at different clusters, and we are going to look at a cluster which gives me the lowest free energy, because in some sense that is the most optimal cluster for this system. Okay, and we take those clusters. And by the way, for hydroxide, we did this. Initially, it was considered a little bit of a controversy for hydroxide, but spectroscopy and thermochemical studies bore out our estimation that it should be 3-coordinate. And it also turns out to be consistent with ab initio molecular simulations. So now that we have an optimal cluster, okay, and we choose the optimal cluster just to make the calculations work out nicely, or with all the approximations that we are building in. And we can go ahead and we did the same kind of approach for all the other ions. And here are some results that we are showing. And these are thermodynamics of neutral ion pairs. Going from HOH, so a proton and a hydroxide, all the way to potassium and a hydroxide. We are able to get the pair hydration for neutral pairs. And this is a well-defined thermodynamic quantity in extremely good agreement with experiments. For example, we are able to predict at 298 Kelvin the pK of water to within 0.2 units. Okay, and for the problem of sodium-potassium selectivity in the ion channel, this proves to be crucial because we find that sodium is better hydrated, which is not a surprise, and we are able to get the values in good agreement with experiments. For the case of zinc fingers and transition metals, the theory proves rather interesting. So we studied all the transition metals starting from the alkaline earth, bracketed between the alkaline earth calcium to zinc. So in the transition metal, for the transition metal ions, you have to deal with this feature of the d orbitals, which are degenerate for a transition metal in vapor. These d orbitals are degenerate, but once you put it in liquid water, this degeneracy is lifted. They are actually, the d orbitals will split in the field set up by the hydrating water molecules. And so this splitting leads to this kind of very interesting biphasic behavior. Okay, manganese has 5 electrons in one of these orbitals. So manganese does not show the splitting behavior. Neither does zinc, nor does calcium. But all the intermediate ions will show the effect of the splitting of the d orbital. And we can readily take out the behavior of the splitting. Either you can get this delta from spectroscopy or from electronic structure methods. And what you find out is that the splitting depends on, the radius of the particle depends on essentially the shielding, the atomic number minus the shielding constant. This is a standard result that goes back to Linus Pauling. And from that, you find out that the hydration free energy of the particle, of the ion without any of these d orbital splitting, should go as just with the proportional to the atomic number. As I said, we can get out this the splitting contribution of splitting from spectroscopy studies and remove it from our calculation. And once you remove it from the calculation, we see that we are able to match the trends that are predicted without ligand field effects. And going back to the problem of zinc versus iron, it is precisely this physics that prevents iron from entering the zinc finger, even though iron is in much higher concentration. Okay, so this was an overview of what I wanted to talk about ions. In the next part, I'm going to focus exclusively on proteins, and this is much more recent work. Okay, so in proteins, the question has been, or the question that motivates our work, is to understand the phase behavior. Okay, so we are interested in this question. Okay, what is the free energy if I take a protein from vapor and stick it into liquid water? Okay, and this question, and for small solutes, this is very well understood. This question of free energy of transfer from there being no solvent to the solvent phase underlies numerous problems, starting from phase behavior, aggregation, and so on. So the question is, what is the partial molar Gibbs free energy of the protein in solvent? So the state of the art till about 2011 was very beautifully summarized by Arya Ben Naim in his book, where he notes the following. He says, okay, we turn to this discussion of the solvation Gibbs energy of real proteins. This is an extremely complicated subject. No one has ever measured it or calculated it for any real protein. Okay, and it is because of this inability to actually characterize the hydration free energy of these molecules. What has happened is, since the very beginning of our studies in protein solution thermodynamics, starting from the work done by, say, Etzel and Kotzmann, the approximation has been to treat the free energy as an additive sum of terms. Okay, so for example, here is a schematic I'm showing. So I have a reference peptide, and I add to it a side chain. And the belief is, okay, the target free energy of this, the free energy of hydration of this target peptide can be given by a weighted sum. Typically, the weight factors are proportional to the surface area of exposure of these constituent groups. Okay, so this is a foundational idea in all of protein solution thermodynamics. Okay. And so do keep this in mind, that the hydration of a macromolecule in this foundational idea is treated as a sum over constituent parts. So so this idea of, hey, I can add up all the pieces together and describe the hydration of the protein has also impacted our understanding of temperature effects. So here is a schematic, and this schematic was motivated by what Kotzmann writes in his very influential review. So let's say we are interested in understanding the association of two proteins. Okay, these are two helices that I'm drawing. So what he would argue, and what the standard picture would argue is, okay, there are these hydrophobic groups, and here is a schematic from Creighton, and here is another schematic from Bill's text. So what we are asked to imagine is water is somehow ordered around the solute. And the reason for this ordering, I'll explain in a minute. Reason for assuming this ordering, I'll explain in a minute. And so the model or the framework that is proposed is when these solutes come together in solvent, the ordered water molecules are somehow released. Okay, and so that is essentially what is driving the association. So for exposed hydrophobic groups, the assumption of ordered water molecules is interpreted to mean that the hydration entropy is negative, and this release is again, I mean, the hydration entropy being negative, and when the system is heated up, these ordered water molecules are assumed to be released. And so the heat capacity is assumed to be positive. And these processes are then assumed to be driven in the direction because of in increasing temperature. So the assumption is, as I increase temperature, hydrophobic hydration is enhanced. Again, all of these ideas are being driven by, are coming from extrapolating from these simple molecules, simple solutes in water onto the protein. Okay, and in the case of protein folding, which is what we will focus shortly, the same idea is implicit here. So I have now an unfolded polypeptide. We are asked to believe that the hydrophobic groups, so the hydrophobic groups are obviously in water, and when the protein collapses, we are asked to believe that, okay, all these ordered water molecules are released, and that is what is driving the folding. Okay, and if you were to do this process in reverse, what is then predicted, and this is also seen experimentally, is cooling should promote denaturation. So this is seen experimentally. So this is taken as a confirmation that, hey, I mean, hydrophobic hydration is in fact driving this process. So remember these two signs, that the entropy of hydration is negative because the free energy profile in this process is positive, and heat capacity is positive. Okay, so that is the standard picture. So let's see what theory predicts for this. So what we started doing when we, back in 2012, we took a first step in saying, okay, let's try to model the free energy of hydration free energy of a protein. Okay. And this was our first attack, and we did this for a protein cytochrome C. Okay, and we learned a lot from that initial study. It was not a perfect study by any means, but from that initial step, we figured out a lot of issues. And later iterations of the theory, we refined the theory to better account for the shape of the protein. Okay, so these draw from the work of my former students and both at JHU. Okay, so now we imagine the following: we have a solvent water, we have a box of solvent, and we are going to create a cavity in the shape of the protein. This black object with nubs or with corrugated object is going to hold our protein. And I'm going to do the exact same I did for the ions. I'm going to stick the protein in this, assess all the long range effects, and I then close the inertial slowly. Now I'm going to do all these operations in a practical simulation. These are all based on classical force fields using charm force fields and standard solvent models. The way I'm going to apply this, create the cavity, is to sit on each of the heavy atoms and apply essentially a WCA potential to move the solvent interface outwards. Okay, so I'm applying a field that essentially moves the solvent I can modulate the solvent interface. And in doing so, I can get all of these quantities, okay? All of these quantities. So having developed this idea so far, we can also do the following. We can get both the excess enthalpy. Standardly, it is obtained in the following way. We have a box of solvent molecules. We stick the solute in that. There is a reorganization of the solvent around the solute. You can try and compute this as a direct difference between the potential energies in this and this these two systems. We don't do that. We are a little bit more cognizant of statistical issues. So we are going to look at the neighborhood and slowly converge it to the bulk limit. Okay, so we can make good estimations of the reorganization contribution and the direct solute solvent contribution. We can get the entropy directly from Euler's relationship, neglecting pressure volume and thermal expansivity corrections. And we also make a couple of checks. So we can compute this quantity from an excess enthalpy. I can also compute the entropy as a temperature derivative. Okay, so I'm going to have a check on my entropy calculations. And I'm likewise going to have a check on my heat capacity calculations. So I'm setting the stage for you, because the results in anticipation of what I'm going to show you, I'm setting the stage here to emphasize that we run multiple checks to make sure the numbers we are getting and the trends we are getting is sensible. Okay. So let's look at first a prototypical hydrophobe, which is methane. So this is looking at the free energy. That is the free energy of methane as a function of temperature, the black pentagons. And I can look at the different contributions. That is a solvent exclusion contribution. It's slightly increasing with temperature. This is the chemistry contribution that also increases with temperature, although that increases with temperature. And that is the long range contribution. Notice that the long range contribution is negative, but the solvent exclusion, the revised chemistry contribution is positive. This is already giving us a hint that in the case of a prototypical small hydrophobe such as methane, water is actually being pushed into contact with the solute particle. Okay, rather than the solvent having attractive pulling the solvent attracting the solvent. Okay, so the solvent is being pushed or compressing the solute particle. Okay, so important point here is mu excess is increases with temperature for all components. Okay, so from this you can easily conclude that excess entropy is negative, and to get the excess enthalpy trends, we can look at both the excess enthalpy, okay, from direct calculations, and the excess entropy. And these contributions here, and in parenthesis, I'm showing the heat capacities from the two different pathways. They agree within statistical uncertainties. This was our estimation of the entropy from a temperature derivative. Within error bars, it does agree. And what we find for methane is the excess entropy of hydration is going to be negative, and it is lower than, is more negative than the excess enthalpy, which is also less than 0. Okay. So here is so that also rationalizes the heat capacity trend, which is so all of the signatures so far for methane are conforming to the standard picture of the hydrophobic hydration of a solute particle of these solutes. But if you go down a little bit and look at different contributions to the enthalpy, you find the following. Indeed, it is true for methane that the reorganization term is the dominant contribution to hydration, to the enthalpy of hydration. But the excess, there is the solute solvent contribution also plays an important role, albeit to a lesser extent than the reorganization contribution. So here is the first sign that we see that even for a prototypical hydrophobe, solute solvent interactions are playing a non-negligible role. So now we do this for a protein. We go ahead and look at a deca-alanine helix in our simulation. And so again, these are all coming from standard free energy, standard force field calculation. That trend, that is the excess chemical potential of hydration as a function of temperature. So it is increasing exactly as you saw for a hydrophobic solute, methane. It increases with temperature. And I'm plotting all of these values relative to the value at 282 Kelvin just for ease of viewing. Okay. Notice one thing, that this behavior is now dominated by attractive interactions. Okay. The packing contribution or the solvent exclusion contribution, I'll come to in a minute. And just as this is a sanity check of our calculations, now what you see, there is a reversal. The enthalpy of hydration is more negative, okay, versus entropy. And again, consistency checks are obeyed. Notice the reorganization term is much, much smaller than what we get from direct solute solvent attraction. Okay, so solute solvent reorganization term is much less or much lower magnitude than solute solvent attraction contributions for this particular for this decahelinin helix. And we have done this for different systems, for coil conformers, for combination of helices. The trends are roughly the same. Okay, so trends are matched. So here is comparing these objects side by side. So what you find for methane is the solvent exclusion increases with temperature. Okay, but for a helix, it decreases with temperature. Okay, so the entire idea of additivity right here, it fails. Okay, so you cannot, and even at the point of looking at just cavity contributions, additivity fails. In published work, we have also shown the failure of additivity in looking at just attractive contributions as well. So the first important conclusion you come to is using small molecule analog to look at hydration of proteins will have conceptual limitations. Okay, so how do we rationalize the temperature effects? Okay, if I don't have to appeal to these models of, hey, water is organizing and ordering in this way or that way. Once again, theory helps us in this regard. Theory asks us to look at the coordination distribution. Okay, so when I look at the coordination distribution at 314 Kelvin and 282 Kelvin, we find the following, that the coordination distribution moves to the left. So fewer number of particles are inside the inner shell of the solute. So as I heat up the system, the solvent is expanding, the population is decreasing in the inner shell. And if I look at the binding energy motivated by theory, if I look at the binding energy versus coordination number, what you find is at higher temperatures, the binding energy is higher relative to the temperature and binding energy at a lower temperature. And for the same occupation state, the hydration, the binding energy is going to be lower, and this distribution is also shifted to the left. So the explanation for all these hydrophobic signatures is rather simple. As you increase temperature, the binding energy becomes less favorable, population decreases. Quasi-chemical theory then standardly tells you that the chemical potential should increase with temperature and so must the enthalpy. And then you straightforwardly get that the heat capacity should be positive and the entropy should be negative. Okay, and so we don't have to make any appeals to peptide hydrophobicity and for explaining any of these trends. So let's see the impact of this in the remaining 10 minutes. Let's see the impact of this for understanding problems related to conformational transitions in proteins. Okay. So this part was actually in terms of chronological order. This work was done before the work that I just showed you on temperature effects. But although we had all the temperature effects in hand when we were studying these problems, this problem is related to this whole issue of protein non-folding. This was a fairly dramatic and important a groundbreaking discovery that you have sequences in the protein sequences that do not fold, that are intrinsically disordered. Okay, and what Iversky and Dunker showed, and they have argued, and again all this argument is based on the standard picture going back to Kotzmann on dominant forces in hydration in protein solution thermodynamics. The typical way to see this is mean charge versus mean hydrophobicity. And they see this, there is this beautiful trend. They see that there is a partitioning, or there is, at least to the eye, you can eyeball and say, hey, there is a partitioning between disordered and folded structures. And there is also, you see a pattern, okay? So going from serine onto glycine, these are thought to be disordered. These are thought to be prevalent in intrinsically disordered structures. And obviously the charged residues are predominant in intrinsic disorder. If I have more of the hydrophobic residues, you tend to form collapsed structures. So that was the idea. But what was found experimentally was the following. You can take glycine serine peptides and you can form, they seem to collapse. And the authors argued, hey, it looks like it is collapsing. The chains are collapsing, and they argued that it was due to intramolecular hydrogen bonds. Okay, and you see similar trends with other glycine only peptides, or even polyQ peptides. Okay, so trying to rationalize this trend, one of the ideas was, okay, I mean, these chains are collapsing perhaps because of hydrophobic effects. Okay, so this was an important work that came out of Rohit Papu's group, where they try to model these peptides using their simulation framework. Okay, so we thought of looking at this problem from the perspective of quasi-chemical approach, and we looked at the collapse transition of a glycine 15 peptide. And for which we had, there was extensive simulation data. I mean, these were very, very long simulation, microsecond long simulations that came out of that Dikti Karandur, Harris and Monty Pettit had published. And those are shown by these circles here. So what I did was I looked at this collapse transition of this glycine polyglycine using adaptive bias force method. So essentially, I'm using biasing forces to collapse this peptide and look at the free energy change. And with care and attention, we found that our adaptive biasing force methods with with much less aggressive simulations agrees very well with what Pettit had published using far more aggressive sampling. And I also did the following. I did the same calculation without the solvent. And in that case, what you find is there is a fair amount of drive to collapse. So right here, you see that solvent should inhibit, not drive the collapse transition. Right here, just at this stage of the analysis, you immediately say that hydration should be driving this process, not the converse process. So now let's take a look at how does hydration drive this process. So to do that, we are going to refine the theory a bit more. What we are interested in is the free energy change, and we are going to look at the vacuum contribution without the solvent and the solvent-solvent contribution. Okay, so I'm going to look at this, the potential of mean force between two, free energy change between 2 points. And I'm going to partition it standardly, as you might do for two methane particles, between a solvent-only contribution and a solute-only contribution. And those are the values of my reaction coordinate. Okay, so which I take. And now we appeal to we go back to our quasi-chemical framework and ask the question, okay, I have for a given end-to-end distance of the polymer chain, how am I going to get the free energy of this sample? Okay, and we can do this. If I have one order parameter as the end-to-end distance, I can take the other order parameter as anything else, and it proves useful to take the radius of gyration as the other order parameter. And we can get the free energy of this object as again as a multi-state generalization of the potential distribution theorem. And we are going to make an approximation here. Okay, so then what we did was we looked at the radius of distribution for the different values of the end-to-end distance. What you find is the most collapsed structure, the difference between the most collapsed structure versus the more populated structure is only about 2 kTs. But in this little transition, the free energy change, the hydration free energy change, which is always negative, is far higher. So what we find is I can partition I can rewrite my potential distribution relationship in this form. And we can argue based on the data that we have that this contribution should be very small or relatively small. So I can get a free energy bound to my free energy for this unfolded ensemble at 2 different endpoints from just looking at the collapsed conformation. Okay, so and we make the following assumption that the solvent-solvent contribution can be just obtained by looking at only 2 structures instead of trying to sample over an ensemble of structures, which was computationally very demanding. And we can use this approach, and just to give you an estimate, the free energy based on this approximation works out to be minus 5.8 plus or minus 2. And you can do the ABF looking at the entire ensemble average. And we are very close to the target value of that is predicted by it's coming from the alternative approach. So now we can go ahead and look at the different contributions to the free energy coming from, so on the left-hand panel, I'm showing the enthalpy entropy contributions. So what you find is the solvent solute attraction far dominates anything else that you see in the system. Okay, so that is exactly what is driving the unfolding of the chain. So the hydrophobic collapse, hydrophobic mechanism, which was thought to actually collapse the structure, is really not what is happening, but instead the collapse is coming directly from intramolecular interactions. Okay. And the other insight that we got from this is protein solvent attraction becomes we have to acknowledge it in understanding intrinsic disorder. Okay. How much time do I have?
5 minutes. So leave some time for questions. Is it important?
Okay. So that was our analysis for the conformational stability of glycine peptides. And so we have seen this, we have done these kinds of studies for different complexes. We have looked at simple association of simple peptides. Okay. Let me again, the main idea that emerges from all of this work is hydrophobic hydration is overwhelmed by hydrophilic contribution. So it is an inversion or the reversal of the paradigm that we are all used to in at least thinking about proteins in liquid water. Okay. The final part of my simulation, and this is still ongoing work, deals with this kind of these peptides or these proteins, which are called chimeric or metamorphic proteins. Okay, when this study came out, this was a shock to the community, where the scientists in this group essentially could take one 3-helix bundle, they make one residue mutation, and the entire conformation flips. Okay, so it's a fairly dramatic indication of how with just one residue mutation, you can get a conformational change of the protein. Okay. We decided to look at this structure first. We decided to see if we can model this, and we couldn't. Okay, so we couldn't, and now we know why. And let me try to explain that in the remaining time. Okay, so what we found out, all our initial studies were with a small solvent box. Okay, and none of the studies, the results were proving to be where we could prove, we could we could capture the trend. It turned out on a hunch, we started looking at different system sizes, and you could see the following important trend, that hydrophobic hydration is weaker in a larger simulation cell. So we did this for 4,000 watt, for about 5,000 water molecules going up to 31,000 water molecules. You see a systematic decrease in hydrophobic hydration becomes less and less unfavorable. And conversely, hydrophilic hydration also becomes weaker. Okay, and it is again, this is the trend that is preventing, that was inhibiting that was playing havoc in our calculations. So the important point here is a fairly large simulation cell would be necessary to better capture the balance of these effects for such a big object. Okay, so let me summarize, and I hope I have showed you going from just the initial parts of how at least one way of looking at the theory, that the molecular quasi-chemical framework is a rigorous and transparent framework to look at, to conceptualize interactions in liquid water. And it works within both force field-based simulations and ab initio simulations. And that's what we did for ions. For in the case of proteins, we are now able to understand protein hydration without appeal to any additive approximations. And this has important implications. Importantly, the very notion of how we interpret the temperature signatures, we are arguing that these should be reconsidered. Okay, so we believe the signatures that are attributed to hydrophobicity are much simply explained based on hydrophilic interactions. And so this work has been, I've had a very productive collaborations with a lot of people. The work itself was done primarily by my graduate students at Hopkins and my long-term collaborators, Michael Politis and Lawrence Pratt. The theory initially was part of the theories the ideas that I showed were developed by Safir and adapted by Dheeraj for his work on proteins. At Rice, I have a rich collaboration, and we are with Vinny and with Amanda, we are looking at polyamphalite complexes. And with Thiago and Arjun, we are adapting the same ideas and looking at hydration of solid surfaces. And a more recent collaboration that we are striking up is with Chase and Bramy Linhoff, and taking these ideas and looking at chromatographic separations. And all of this work has benefited greatly from encouragement and thoughtful comments from many of my collaborators, Monty, George, Tom Beck, Arya Ben Naim, and Chris Jarzinski. And we couldn't have done anything without the computing support that we got from NERSC and TAC. So thank you for this opportunity once again, and I'm happy to answer any questions.
Thank you so much, Professor Asthagiri. It's a pleasure to have you here with us. We are now open for questions. So
and I need to look at the chat window, I suppose. Where do I see the chat window? Okay, somebody sent a chat to me. Oh yeah, okay.
Can I start?
Sure. Go ahead.
Can I start?
Yeah, please. I mean, I'm ready.
Yes, Fred.
Yeah.
Go on, Fred.
Okay. Thank you for very nice presentation. I enjoy a lot. Let I ask you, I'm just a puzzle. Is it not expected that for large molecules in water, this cavity-free energy decrease with temperature? I expect that if I'm not wrong, David Chandler shown that the free energy for large molecules should depend should be proportional to the interface tension, and the interface tension is decreased with temperature. So we expect for large cavity the free energy decrease with temperature, and it is not the same for small cavities. The small cavity free energy should be proportional to the volume of the particles.
That is absolutely correct. And I was actually looking for if Lawrence was still online, and I think he has dropped off. You're right. You're right. And so actually, even before David Chandler, the idea here goes back to Stillinger. In scale particle models, you will see that you will see that for larger cavities, there should be a difference in behavior. And that is true. So that is expected. That is expected, no question about it. But I don't believe it has been shown clearly for protein systems. And more importantly, you're right about the expectation of this behavior is correct. Going back to the work of Stillinger, and then David Chandler showed, and I was looking for Lawrence because we have some concerns about some of the work. But yes, I mean, we'll granted that it is that this is expected. This trend is expected if you take account of theory. But the whole temperature signature itself, that trend is a new finding. And one other comment that I would want to make is you have standard. So in a standard approach, such as say generalized Born with surface accessible model, that is still assuming the way that, okay, I mean, if I have that is still attributing the signatures themselves, these kind of signatures. Where did I have my entropy signature? Entropy signatures. For example, this signature, the negative entropy signature, to ordering of water molecules, and we find that is really not necessary to. You don't need to appeal to any of that to explain this behavior. Okay.
Okay. Thank you. The second question is how to take in account separate these free energy calculations. I think it's very interesting, but I mean, for a protein that you may change when you move from a gas phase to a liquid phase, it may and should change the conformation. So maybe the cavity should change during this process.
That's again an interesting point. So what we are doing. So let's go back. Let's go back to this case. Okay, I'm taking this as an example. So obviously the protein is in liquid. It is adopting various different conformations. Yeah, and I can momentarily freeze and look at only particular conformations. So if I fix my attention to particular conformations, what I'm doing is in this framework. The framework allows me to go over all conformations. This is for one. I fix attention on just one conformation and look at the hydration free energy of that one conformation. You're right. I mean, this whole process of going from vapor to liquid is just to motivate this or introduce this idea of a hydration free energy. But when I'm doing this, I'm looking at individual conformations. So in principle, we can model all that. We can predict that. So the point of conformational sampling is a good one, and we would do it this way, and we can sum over different conformations that we see. There was a hand up. Is Richard?
Thank you.
It's hard for me to see what's going on the Zoom. So go ahead, please.
Yes, I had my hand up. Yes, this is Richard Elliott.
Oh, hi, Richard. How are you?
Very good. How are you?
Doing
so
okay.
I had 3 questions. First, Well, I'll just mention that I've read the whole book by Beck and Politis and Pratt. Okay, so that's my primary reference. I'm not sure I could pass an exam on this subject, but I did make my best effort. Now, and then in the title of your, and I've also been studying Guggenheim. I read Guggenheim's book, his whole book about quasi-chemical theory, Mixtures, the book called Mixtures. Mm-hmm. And so I'm kind of trying to put these things together and just so that I refer to it correctly, are you referring to this version as molecular quantum quasi-chemical theory to distinguish it from the original Guggenheim's quasi-chemical theory?
That's exactly right. And in fact, that's exactly right. I will go ahead and make this following point, that if you were to do this on a lattice, the same way as Guggenheim would do, you should obviously get all of Guggenheim's results back. So and in fact, Lawrence is back on Zoom. He does that in the book, I believe.
Okay. Well, but still you would miss second order effects, and which Guggenheim looked at in his book, and he said, okay, they're not important. I mean, next nearest neighbors effect.
So if I were to do that for a lattice model, but in my case, I'm not missing anything because I'm accounting for all the interactions locally, and because this is a disordered medium. I mean, so I'm accounting for all interactions in my simulation framework. So I'm not missing any effects. Okay.
Right. But he misses those. But he calculated them on the lattice anyway, and said that they were negligible. But you're finding they're non-negligible.
In for ions and so on, no, they won't be negligible.
Oh, okay. It's got to do with the ions. Okay. But for dispersion forces, it would still be negligible.
For dispersion level interactions, I don't want to commit to an answer and say it is going to be negligible. We have looked at, for example, we have looked at CF4, tetrafluoromethane, and long range effects in the hydration of that object do prove to be fairly important. So I wouldn't implicitly say, hey, I'm going to neglect it. Okay. I would say that is a little bit of a dangerous step that I'm not willing to take right now.
Okay, good. You had mentioned, this is a little different way of looking at things. You had mentioned that some of the work that Walter Chapman and Marshall Bennett have been working on lately with I think it is TPT-N, whereas TPT-1 is, just the first order Wertheim's theory. The later things have been multi-body or in-body effects incorporating those.
So the n-body theory, the multi-body theory. So Ben Marshall looked at TPT-1 and TPT-2, so that is where they stopped. So after that, with Arti Bansal was playing with TPT-2. But then what we did was, in my effort to understand what was going on in SAFT, exactly as you are trying to understand what is going on in quasi-chemical, I was trying to understand what is going on in SAFT. So I tried to derive certain relationships within the Wertheim framework using QCT. And that is, so what that entire approach led to was to look at, so you can look at one body correlation or two body correlation. Quasi-chemical will tell you, hey, I can look at the total n-body correlation of or the total look at multi-body effects around the central particle. I just have to construct those probability distributions. Going back here, the picture may not be the picture. I mean, this is not exactly relevant to your problem, but if I can construct these probability distributions, I can insert that within the SAFT framework. That is what we showed, and that's what is going on right now. I think that was what Arti did, and the subsequent students have been looking at that approach to use ideas built on. Sorry.
Opa, Davi. Opa, tudo bem? Desculpa aí atrasar pouquinho.
What's going on? Sorry.
Na verdade, ainda está acontecendo, mas eu já falei minha parte.
Was it satisfactory, Richard?
Yeah, I got a little confused towards the end there. There was something going on.
Please continue, Professor. It was a little disturbance from Professor Fred.
Okay. So as you were mentioning, so there has been TPT1 and TPT2, and Ben did this very nice work of looking at two-body effects. With Aarti Bansal, as I said, I was trying to look at this whole SAFT framework from the viewpoint of quasi-chemical, and that effort was taken over by Aarti Bansal, and we realized, hey, instead of looking at one particle, two particle on the central sphere to get my so the framework is built around hard spheres and packing around hard spheres. I can look at one hard sphere and look at all the different n contributions of other solvent particles around the central hard sphere. Essentially, we are trying to characterize this probability distribution. If that is my solute, and within the SAFT framework, then this would be the bonding volume, and we are trying to look at the distribution of particles in the reference system in this bonding volume. And we can use quasi-chemical ideas to generate those probability distributions that are then taken over into the SAFT framework. That is what is leading to the multi-body theory.
Okay, but I guess that makes sense for proteins, but for, small molecules, you wouldn't have hydrogen bonding sites all around. Well, you got 4 on water, but that's kind of the exception, right?
Right, but these were for the way I think the way the multi-body theory, reference theory has worked out so far is we are now looking at just packing around hard spheres. So that this solute is a hard sphere. Sorry, this solute is a this solute is a hard sphere, and I'm just looking at packing around a hard sphere. In TPT1, what you're looking at is just this correlation. In TPT2, you're looking at the 3 particle, and now with ideas borrowed from QCT, from quasi-chemical, you can look at all the n coordinate states, going from n equal to 0 up to whatever the n number that you're looking for. And there, so that is, we figured out a way to build those probability distributions for the hard sphere reference, and that we take into SAFT. And then it is in the SAFT framework, you're inserting the hydrogen bond in the hydrogen bonding and so on, in the association and so on.
But the only reason you do that is to generalize or extend the steric hindrance. Exactly. That's okay. Right. That's right. And actually, if Walter is here, he can add a little bit more, but that's exactly what we are trying to do. But steric hindrance is, for really high, for things that are, orientationally specific, steric hindrance is a good approximation. So two particles. So here is what happens. Going back to, if I'm trying to remember Ben Marshall's work on this, what you see in Ben Marshall's work is if you go to higher and higher densities, you start seeing deviations. So the one particle correlation doesn't do a good job. 2 particles starts to fail, but the multi-body effect starts to still behaves in better agreement with simulations. So, and you're right. So I think your intuition is correct in the sense that at higher densities, at lower density, you should be able to get away with 1 and 2 particle correlations, but at higher densities, and ultimately our view, this is maybe a distant hope, we can try to build a theory of electrolytes for these systems, for these kinds of, within a SAFT kind of framework. We don't know if it's going to work or not, but that's a hope. That's what we are trying to do. I see. If it literally was a point charge, then you would need that. Steric hindrance would not be a good approximation. You would need multi-body effects. That's right. Right. Okay. So this is a slightly different question, but in my process, in my study of these different, trying to compare them, different perspectives, what I did was I said, let's just look at what I call a strong solvation. Okay, so you just have an acceptor on one molecule and a donor on another molecule. So they're 2 distinct molecules, right? well, we can think of them as acetone and chloroform with all the dispersion forces removed, and they're exactly the same size. Okay, so just keeping it really simple.
Mhm.
Now, when I apply that model as best as I can understand it to Guggenheim's QCT, then it looks like he's missing the term that comes out. So if you look at Wertheim's theory, that would come out as the Helmholtz energy change is equal to just the ln of x,
Mhm.
where x is the mole fraction of monomer, of unbonded sites. Okay,
Unbonded sites. Mhm.
and then Wertheim's theory adds another term that's 1 minus this, I'm going to call it x again, okay?
Mhm.
1 minus x over 2.
Mhm.
So Wertheim's theory has that 1 minus x over 2, and it's hard to say what the Helmholtz energy is. And well, I mean, Guggenheim does derive it. It's complicated, but it's not that simple 1 minus x over 2 contribution. And so when you try to actually compare these two things and calculate your internal energy, what you see is that extra term that comes from Wertheim's theory gives you a much stronger internal energy at high beta W, the binding energy.
Binding energies. Mhm.
Whereas QCT, it just sort of, yeah, it's going down, it's concave down as you go, to lower temperatures, but it's not nearly that. After you get to about beta W equals 3, then the QCT is kind of just continuing to go down, and that extra term in Wertheim's theory takes a sharp dive. They become very different. So have you ever, I mean, probably you haven't, but would your theory pick up on that? Or
so the beautiful questions. I mean, and I can see. I'm not going to be able to say, hey, this is what is happening, because some of the issues that you're facing with are the issues that I had when I was trying to understand the SAFT framework from the perspective of QCT. This approach that we sketch here, this should obviously pick it up. I mean, whatever I'm sketching on this is, I mean, this equation here, for example, that's an identity. This should obviously hold. I mean, if you're able to calculate all of these quantities correctly, yes, it should hold. So going back to this issue of this 1 over the half term that you were mentioning, that was one of the things that was troubling me. And I don't pretend that I have been able to derive it exactly from the point of view of QCT. What I did, what the log x term easily comes out if you take the fluid itself, the solvent, as non-interacting. So these are just hot spheres. They're just steric exclusion. So that does work out, but so no, I mean, I'm wandering in my answer to you because I don't have a precise what the issues you're facing are, I think, important. But going back to, if you're able to explain the physics of the system that you are mentioning, this theory should work. I mean, this is standardly it'll work because that's an identity. If you put all the pieces in together, it should certainly work. But how to derive it, how to develop analytical expressions is, I think, still an open question. And what I had been trying to do, let me go to the ion case. I have been trying to construct these cluster integrals. These ratios are cluster integrals, and trying to simplify them, but I have not been able to make much progress for the most general problem of trying to rederive all of Wertheim in the QCT framework.
Oh, okay. I have one more sort of far afield question, if I can.
Please, go ahead.
So there's a whole different, well, I don't know how different it is, kind of theories, the Cosmo RS theory. Have you studied that at all?
I have to be.
So let me mention the connection with QCT is best described in the appendix of the Sandler and Len paper, where he derives the expressions for the activity coefficients with an argument that looks like QCT to me. And so,
So, I mean, I would make, so you again, this is, I have studiously avoided Cosmo RS for different reasons, because the whole idea of Cosmo RS trying to partition electron densities and so on, I find it to be having done electronic structure, I find it very difficult to comprehend. So I have not gone through that path. I would make one important distinction, and I do know some of the arguments that Sandler made in his work long ago. I think there was an argument between Sandler and also the Cosmo people on some of these approximations. Those are all, I mean, but that QCT, just for reference, that is Guggenheim QCT. That's not what we are. I would say that is different from the molecular QCT that we are trying to do.
oh yeah. I'm not saying, yeah, I'm trying to distinguish QCT from MQCT here. When I say QCT, I mean Guggenheim QCT.
So yeah, I mean, I think, but yeah, I mean, to answer your question, I am very nervous about Cosmo RS and that approach. I mean, it seems to do fantastic. I mean, they seem to explain data quite well, but I cannot pretend to say I understand that.
Yeah, I'm making a distinction between their, the quantum mechanics and the way that they get these, polarization surface energies, and then they take those surface energies, and then the second step is they use QCT to get the activity coefficients and the free energy.
And if I remember the discussions long ago, that the distinction that Sandler was trying to make is Sandler was trying to be a little bit more careful in terms of the permutations involved with these polarization contributions, if I'm not mistaken.
That sounds right. And yeah. And so it sounds to me, to the extent that it is like QCT, that it might actually be a kind of a basis for saying, okay, that's a sort of modernized off lattice sort of QCT, and then add some features onto that, and maybe it's another way of coming at the problem. But I was just wondering what you sound skeptical though.
No, I don't know. When I say I wouldn't say it's, I mean, I don't want to even take any position on this on this Cosmo RS business. I mean, I know Walter wanted me to think about Cosmo RS. I mean, I'm happier thinking about, I want to deal with proper molecules and proper, stick with things I understand better. These polarization surfaces and all are things I have not understood well enough.
Well, in the last chapter or so of Guggenheim's book, he does lay out, the QCT for these, he calls them surface elements. Sandler calls them surface segments. The concept is exactly the same.
I'll take a look at those, definitely.
Okay, yeah, it's wonderful. Thank you so much for your presentation.
Thank you very much. Yep.
Would anyone else like to ask a question?
Can I ask a clarification?
Yes, please, go ahead.
Please go ahead, Professor.
You made about solvents like water. Can you make some comments on normal alkane solvents like, say, hexadecane, for example? You said methane thing. Will such thing will work for straight chain alkane solvents also?
So, sorry, so you're asking me, will our approach work for straight chain alkanes?
Yes, a solvent.
Yeah, so I have not done that work myself, but we can certainly do this. We can. So from the perspective of the theory, and I'm just doing this as a schematic now. This solvent can be anything. This particle can be anything. You can do certainly you can do alkanes. We have Arjun has looked at solubility of oxygen in an alkane system using these ideas, and you can certainly do it. One of our students locally has done this for when these particles, the blue spheres are supposed to be solvent. I have looked at only water, but you can certainly look at alkanes. That's not a problem. All you have to do is just how you do you have to be careful in how you do the counting. That's all we need to do.
Okay, thank you.
Apply the theory for that.
Any more questions? Okay, so once again, thank you so much, Professor Asthagiri, for this nice presentation.
Thank you very
Please.
much.
Thank you.